Hello friends, I hope you all are safe. Stay home, stay safe, and I wish you all the best during this challenging time. Okay, today we are going to discuss about the module rotational dynamics 1 and 2. Actually, these are the two different modules, but the contents which are included in the same one. Here in the introduction, the different quantities in the rotational motion, they are analogous to the quantities which are available in a translational motion. Like angular displacement is analogous to the linear displacement, angular velocity is analogous to the linear velocity, angular acceleration analogous to linear acceleration, and torque is analogous to the force. So in this way, we can say that the different quantities which are observed in the rotational motion, they are analogous to the quantities which are observed in the translational motion. While, while studying this rotational dynamics, we shall consider the two important conditions as a moment of inertia and angular momentum. So let us start with the moment of inertia. But before starting to the moment of inertia, we should know the difference between inertia and moment of inertia. Or what is meant by the inertia and moment of inertia? So, as we know, our body is moving uniformly along the straight line. So when it moves along the straight line, it has a tendency to oppose any change in its state of linear motion. Means when once it starts with the linear motion, it does not allow to change in its state of linear motion. That property is called as the inertia, and that inertia is represented by the mass of that body. Now, how to say that? If we take the number of balls, if the one ball is leather, second one is suppose tennis ball, third one is plastic ball, and last one is a thermocol ball. All the balls are having the same shape. The shapes are not different, but the masses are different. So greater mass of that body gives the greater inertia, and less mass of the body gives the less inertia. So inertia of the body depends upon the mass of that body as far as the linear motion is concerned. In a similar way, a uniformly rotating body possesses the tendency to oppose any change in its state of rotation. So any rotating bodies also try to move in the same direction, in the same way. So it does not allow to change in its state of rotation. So that property is represented by a quantity. It is known as the moment of inertia. But what is that moment of inertia? How to define or how to state the moment of inertia? So moment of inertia of any body about the axis of rotation is defined as the sum of product of mass of each particle and the square of its distance from the axis of rotation. So this is about the statement of moment of inertia. We'll see how to calculate that value. See, we have one figure. This is a rigid body. A rigid body is made up of a number of atoms or number of tiny particles, and this is the axis of rotation through which the body is rotated, or through in which the axis of rotation the body is rotated. Now if n number of particles are there, m1 is the mass of that first particle, and whose position from the axis of rotation is r1. Second particle whose mass is m2, and the axis of rotation, the distance of that particle from the axis of rotation is r2. Third one is mass m3, and the axis distance of that particle from the axis of rotation is r3. Similarly, we can say here this is the nth particle whose mass is mn, and whose distance from the axis of rotation is rn. So n number of particles are there. N number of particles whose masses are m1, m2, m3 up to mn. The distances are from r1 to rn respectively from the axis of rotation. Then moment of inertia of that body. Initially, we have to find the moment of inertia of first particle. So moment of inertia of the first particle from the axis of rotation is the product of this mass and square of the distance from the axis of rotation. So this is a m1 r1 square. Similarly, moment of inertia of second particle for the same axis of rotation m2 r2 square. So in this way, we can calculate. Now total moment of inertia of the body about the axis of rotation is given by I is equal to m1 r1 square. This is the moment of inertia of first particle. m2 r2 square, moment of inertia of second particle, m3r3 square moment of inertia of third particle, and mn square moment of inertia of nth particle. So summation of all the moment of inertia gives the moment of inertia of this body about the axis of rotation. So we can write this equation: I is equal to summation of I is equal to 1 to n mi ri square. Each term of this summation represent the product of mass of the particle and the square of a distance from the axis of rotation. SI unit of moment of inertia is kg meter square, and its CGS unit is gram centimeter square. Okay, now as we know, if the body is made up of a finite number of particles, then we can find the moment of inertia using this equation. But the moment of inertia is supposed continuously distributed throughout the body. Mass is suppose continuously distributed throughout the body, then this equation is not useful for finding the moment of inertia. So that this equation can be replaced by the integration. So see, if the body is continuously distributed or mass of that body is continuously distributed, then we have to take a small element whose mass is suppose dm. So dm is the mass of that element, and that element whose distance from the axis of rotation is r. Then moment of inertia of that element from that axis of rotation is r square dm, and that equation is r square dm. Then moment of inertia throughout the body or entire body, which is written as I is equal to integration of r square dm. So this equation number 2 can be used to obtain or to get the moment of inertia of any body having the symmetrical shape. So in this way we can find the moment of inertia. Okay, now let us move towards the more kinetic energy of rotating body. How to calculate this kinetic energy of this particular body when axis of rotation passing through the point O. So when body rotates, see, when the body rotates, all the particles of the body revolve in a circular path about the axis of rotation, around that axis of rotation. So on account of this linear velocity, we can say here every particle possesses kinetic energy, and the total kinetic energy of rotating body is equal to summation of all the kinetic energy of all the particles they are present within that body about the axis of rotation. So this is the actual picture. This figure shows that this is the rigid body in which n number of particles are present here. This is the axis of rotation through which the body can rotate. The body rotates with angular velocity omega. So first particle whose mass is m1, the distance of that particle from the axis of rotation is r1. Second particle is m2. From the axis of rotation, the distance of that particle from axis of rotation is r2, and so on. We can calculate all the then total mass of the body. Total mass of the body is the summation of all the masses of all the particles that are present within that body, and they are rotating with the angular velocity omega about the fixed point passing through the O and perpendicular to the plane of figure. Then if there are n number of particles, so these particles are m1, m2, m3 up to mn. They are situated at a distance from the axis of rotations are r1, r2, r3 up to rn respectively. Now all the particles, they are moving in a circular path with the same angular velocity but with the different radii about the axis of rotation. So the linear velocity of the particles are different. So we have to find the linear velocity of first particle. So suppose the first particle of mass m1 revolve along the circular path of radius r1, that is the distance of that particle from the axis of rotation. The linear velocity of that particle is given by v1 is equal to r1 omega. Then kinetic energy of that particle E1 is equal to 1 half m1 v1 square. But we know v1 is r1 omega, so substitute in this equation 1 half m1 in bracket r1 omega bracket square. So we can write 1 half m1 r1 square omega square. Then for the particle, second particle whose mass m2 and the distance from the axis of rotation is r2, and it possesses kinetic energy which is given by E2 is equal to 1 half m2 r2 square omega square. So similar expression can be written for kinetic energy of all the particles. Then total kinetic energy of the body is equal to the summation of kinetic energy of all the particles. And therefore, we can write this equation is equal to E1 plus E2 plus E3 plus up to the En. E1 is 1 half M1 R1 square omega square. Second one, 1 half M2 R2 square omega square. And for last one, M1, 1 half Mn Rn square omega square. Now take common 1 half and omega square. So inside that bracket, only M1 R1 square plus M2 R2 square plus M3 R3 square up to Mn Rn square. So for that we can write here summation of I is equal to 1 to n mi ri square. So that quantity is nothing but the I. So final equation becomes E is equal to 1 half I omega square. So this is the expression for the kinetic energy of uniformly rotating body about the axis of rotation passing through that point O. Now see the motion of rolling body. Suppose the body is a roll. Rolling body possesses translational as well as rotational motion. Translational motion is at the center of mass, and rotational motion is about the axis passing through the center of mass. For example, the coin is rolling on the surface. So what will happen? The center of that coin possesses the translational motion, and all other particles in that coin they are possesses the rotational motion. Therefore, its a kinetic energy is not only the translational kinetic energy. There is always rotational kinetic energy. So we can say that here kinetic energy of that coin or rolling body is equal to the summation of a translational kinetic energy and rotational kinetic energy. So okay, we can write this equation E is equal to Et plus Er. Now suppose m is the mass of that body, r is the radius, r is the radius. Now v with the linear velocity and omega is the angular velocity, and I with the moment of inertia of a body about the axis passing through the center of mass. Then we can write this equation E is equal to now 1 half mv square for the translational kinetic energy, and plus 1 half I omega square is the rotational kinetic energy, and this equation is the total kinetic energy of that body. Now we can write the kinetic energy of rolling body in terms of radius of gyration. So E is equal to 1 half m. Instead of v, we can write here r omega, that is v r square omega square. But for I, we can write here mk square. So 1 half mk square omega square. Now 1 half m omega take common from these two terms, and the remaining part is r square plus k square. So E is equal to 1 half m. Omega is nothing but the v upon r. So instead of omega square, v square upon r square inside the bracket r square plus omega square. And now E is equal to 1 half mv square. Now move inside that bracket. So r square plus k square divided by r square. So and take means shifted in each term, so that we are getting 1 half mv square inside the bracket 1 plus k square upon r square. So these are the equation number 5 and equation number 6 gives the total kinetic energy of rolling body in terms of angular velocity, linear velocity, and radius of gyration. Now move towards the rolling motion of a body without slipping on inclined plane. So this is the inclined plane with the angle of theta, and if the body is kept here at the height h, so initially it's a kinetic energy is zero. Why? Because it is a rest at the top position and it has the potential energy. So that body of mass m, radius o, it rolls down without slipping. That is very important, means there is no friction, a smooth inclined plane making an angle theta. Okay, so when body rolls down, its potential energy is converted into kinetic energy, and while kinetic energy, there is a translational as well as rotational kinetic energy. So as we know that body rolls down on the smooth plane surface, it means that there is no loss of energy during the friction. So when it v be the linear velocity acquiring the body when it reaches at the bottom of the inclined plane, and at that time there is a loss of potential energy which is the same as that of the gain in a kinetic energy. So we can write this equation. This is the potential energy which is at the top, and when it roll down and reaches at the bottom, it acquire the kinetic energy, and these two energies are same. So mgh is equal to 1 half mv square plus 1 half I omega square. So that is equal to 1 half mv square inside the bracket 1 plus k square upon r square. So v square is equal to that twice gh upon 1 plus k square upon r square. So v is equal to under root by GH upon 1 plus k square of mass square. So this is the equation number 7 is the linear velocity of a rolling body when it reaches at the inclined plane. So in this way we can also find the linear acceleration by using this equation. This very